Hi, it's Gary and welcome back to the workshop. Today we're going to talk about bracing plates. And if you remember in episodes 13 and 14, we prepared different types of tops, different types of plates, such as a solid top in episode 13 and a double top in episode 14. And in those episodes I showed you how to use deflection to monitor stiffness and flexibility, but also some other methods such as ways to listen and use a computer to listen to the frequencies that the soundboard plates are giving off when we tap them, and we learn how to flex with our hands. And so we use an integrated approach to get a good sense of what these plates are doing and how they're behaving. And all of this will feed into how they ultimately sound in the final guitar. So in today's episode, I'm going to take this double top plate that I prepared in the previous episode, which is a double top plate that has spruce on the outside and cedar on the inside, and I'm going to show you a typical bracing process that I use. And then after I brace the top, I'm going to show you how I carve those braces. And along the way, we'll use the similar techniques that I showed you in the previous episodes to flex, to listen, and to measure the flexibility in these tops. So you can see the integrated approach that I'm advocating here is that we try to use all of our senses and all of the different techniques that are more of measurement techniques, which are all complementary to give us a lot of information that we can use to steer the physical structure, which will ultimately result in the sound. And all of these methods will be used to correlate to a final sound, so that once we build up these correlations over several guitars that we make, when we go back to build one, using these early measurements and pieces of information, now we can steer the sound quite directly. All right, so the thing that I need to do with this double top plate is a few things. I have the brace pattern drawn out in pencil already, but you'll notice that I have a rosette which I inlaid very strategically and precisely into this double top, and I inlaid it by preparing the rosette and then dropping it in just far enough so that the top of the rosette is at the same level as that of the top. Because with these thin veneers on the outside of a double top, you really have no room to sand from the outside and take off from the outer veneer, so it has to be dropped in quite precisely. So that's what I've managed to do on this soundboard plate, and you notice that it hasn't had the sound hole cut out yet, so that's what I need to do next. And in order to do that, I first need to take this kind of reinforcement that I will place on the inside of the top in the vicinity of the sound hole. So I'm going to glue that tonight, and then tomorrow we'll come back and we'll actually cut the sound hole, which will cut it out of the top as well as this reinforcement. So let's go do that, and then we'll come back tomorrow and we'll talk more about the bracing in specific terms. Now we're ready to go, and I've got the sound hole cut in the soundboard and the reinforcement. And so let me tell you about the bracing system that I'm going to use by showing you what it will look like when we're all done bracing and carving the braces. Here's a look at the bracing system that we're going to construct, and right off the bat I want to emphasize that you don't have to use this pattern, since many different patterns can be successful, especially if you prepare a plate that's conducive with whatever bracing system you're using. There's nothing particularly exotic or earth-shattering about this system, other than, in my hands, it's evolved to this form over time, and it's worked extremely well for solid and double-top soundboards. What is important is that for this video, we use this system as a case study to discuss many principles about how it will behave in terms of feel, sound, and several physical measurements through the whole bracing and brace carving process. A comprehensive set of parameters will be the closest thing that I can give you, short of having you experience it with your own hands and ears. So I encourage you to use the bracing system that works best for you, and use any of the concepts that I show you to your advantage. There's a lot of information in this video, so feel free to skip around the chapters as needed. The main feature of this scheme are 5 fan braces and 2 of what I call auxiliary braces in the middle to give a slight amount of extra support in the middle. These auxiliary braces are not continuous, because while I want some strength in this area when it's under high stress, under string tension, I don't want excessive stiffness either. Along these same lines, you'll notice I use a combination of cedar and spruce bars, which start at 4 by 4 millimeters in cross-section. I use cedar because the stocks I have are slightly more flexible than the spruce ones, and that further helps me to dial in the stiffness that works best for the sound. But I've also used all spruce bracing, and that works fine too if I simply carve off more through the process. But I don't think the wood species is anything you should get hung up on other than in consideration of the stiffness of your brace stock. There are 2 types of transverse braces in the lower bout. There's this one that runs beneath the bridge that's interlocked with the fan braces, and these closing bars at the bottom. These cross braces add stiffness in the cross-grain direction and help solidify the doming in this direction. I've noticed that these 3 transverse bars can clean up the sound at close range to the player, reducing some reverberant, cross-string sympathetic resonances in the body. It's a matter of preference, but some players prefer it, others don't. And speaking of cross-grain stiffness, just be aware that all fan braces, because of their angle of splay, have a certain amount of cross-grain stiffness, which increases as the angle increases, but at the expense of with-grain stiffness. So even a Hauser-style pattern with fan braces only still has cross-grain components. Over here at the lower transverse brace, you can see the arches that inlet the outer fans to the sound hole area. I'm not doing this to increase the vibrating area into the upper bout. It's just a convenient way to extend these braces without having to notch them with the transverse brace. I think it's pretty debatable whether such a small opening would have a sonic effect. You'll notice over here that the upper transverse brace is missing, but that will be added when I glue the top assembly to my back and sides. This is just a feature that facilitates my adjustable action neck system. If you want to copy this bracing process, just add the upper transverse brace at the end. Also here in the upper bout, I have a small amount of reinforcement, and because it's a double top with internal structure, very little is needed in this area. Like I mentioned, this system works really well for solid tops, like on this solid spruce soundboard, and when I use it on a solid top, I simply add a bit more reinforcement in the upper bout. And unlike in this photo, I just want to mention that it's not necessary to extend this transverse brace beyond the outer fans. So that's the tour of our bracing pattern, so now let's get to work. If you remember in episode 14 when I built this double top sandwich, I already started establishing the 28-foot radius in the lower bout by gluing the layers in this workboard, which has a concavity of 28-foot radius. But we're going to continue establishing that radius by using this workboard and gluing these brace elements into the workboard and soundboard by pressing it into and making the braces curve. And when the glue dries, it establishes that curvature by locking in the soundboard plate to the brace. For the lower transverse bar, which sits right below the sound hole, it's too stiff to actually spring in, so I need to radius the bottom of the brace with a routing template. And then this workboard also has a feature in the upper bout where it swoops upward, which will actually swoop downward when we turn the soundboard over when it's completed. And that will facilitate the elevated fingerboard design that I have. But everything from the sound hole up, including this upper transverse brace, which is integrated in my system with the sides and the head block, sits in one flat plane without radius. I'll be using hot hide glue to glue these brace elements, and at this point they're either in a square or rectangular cross section. I prefer hot hide glue because it's really fast, so that it'll set up in a couple of hours, and at that point I can go on to glue another set. So I don't think there's any particular sonic advantage as far as I can tell between something like hot hide glue and synthetic glue, but I think the speed is a particular advantage that makes it really attractive for me. So the one thing that we need to do is throughout this bracing and carving process is I want to show you some physical attributes of the plate and also kind of the sonic characteristics. So like I did in previous episodes, I'll be showing you the deflection and then give you some taps to let you hear what it sounds like through the whole process. So let's do some deflection right now, and then I'll let you listen to some taps. And then we'll move over to the bracing deck and start bracing. For these deflection measurements, which assigns a numerical value to the stiffness of a plate, feel free to review episode 13 where I showed you how to make this deflection rig as well as the theory behind it. But I've got the dial indicator which will tell us how much this plate bends under the standardized weight. So let me set it up and we'll get going. I'm going to start by measuring the width grain deflection of the plate, and you can follow along in the scorecard all the physical parameters as we go. First I'll start by preloading and then zeroing the dial indicator and then load to take the actual deflection. Now I'll change axes and we can measure the cross grain deflection. Preload, 0, and load. Before I start bracing, let me have you hear what this plate sounds like as I tap it. It's not that interesting yet because we have nothing to compare to, but it'll give you a sense of what it starts as. It's rather unfocused, it doesn't have a lot of sustain, but it certainly will be the lowest pitched soundboard that we'll have today, and as we add braces, the pitch will go up because we stiffen the plate, and as we carve those braces, then the pitch will come back down. So let's go over to the bracing deck now and get started. Over here at the bracing deck, I first want to mention that it's important to equilibrate your workshop to the correct relative humidity. And that's because we're going to be locking in structure in the soundboard, especially in the lower bout where we're going to be pressing braces into a dome shape. Now in my workshop, I keep it between 40 and 43% relative humidity, but when I brace, I usually like to have it at 40%, and that's to safeguard against future conditions that players might have their guitars, such as lower relative humidity conditions that potentially are more harmful than higher. Some details about the bracing deck itself. I have plumbing fixtures which are attached to my workbench, and the workbench is a solid core door. And up top I have another piece of solid core door. Down here I use these 2x4 blocks to raise the level of the workboard to the appropriate level. And then we'll be using these bars, these sticks, which I simply make from lumber that you can get at a hardware store. These are sticks made from 3/4 of an inch thick poplar, which I slice these sticks off of, and these sticks are 3/16 of an inch thick. And then they're also 3/4 of an inch longer than this span from the deck to the soundboard. And that gives me the perfect amount of flex and force to apply to the brace. Up top, I also have some sandpaper glued, so that will grab the top of the stick very nicely and keep them stably in place. Over here I have the water bath that's set to 140 degrees Fahrenheit, and I place the hide glue into these little squirt bottles that you can get at an art supply store. And inside I have little stainless steel nuts that keep the temperature constant even when I take a squirt bottle out of the water bath. So everything is equilibrated nicely. The hot hide glue is liquid in this water bath, and that's ready to go. Over here I have an old-fashioned fry pan that I preheat the braces. So this is set to 220 degrees Fahrenheit, and 2 minutes before I apply the glue to a brace, I'll preheat the brace in this fry pan. And what will happen is everything at a warm temperature will keep the glue in a liquid form, because you don't want the hot hide glue to gel, and that's when it loses strength. So by having everything preheated, then my working time is just maximized. And I have about 10 seconds between the time that I apply the glue to putting it down onto the soundboard to make sure that the glue will be strong when it sets. All right, so I'm going to first glue the vertical fan braces, let that set for a couple of hours, and then come back and then glue the next set, which will be the horizontal bars. So why don't we start heating up the first brace in the fry pan and get going. The first fan brace is warm, so we're ready to go, and I'm going to take it out and take some hide glue, and then I'm going to spread a line across the top of the brace. And it's not a huge amount, but it's enough, and I'm going to just spread this bead evenly over the surface and then position it down onto my pencil lines. Now here's the important part. The hide glue can be somewhat slippery before it sets, so I'm going to just hold it down for a moment to let the glue grab, and then I'll apply the sticks. Yeah, that should do it. And I like to apply an even density of the bars. And if you're afraid of it maybe forcing your brace in one direction, you can apply some bars bending in the opposite direction, like that. But if it grabs, usually you don't need to do the different directions. Okay, so that's down and that looks pretty good. It's not moving, and I'm just going to take a stick that has an edge on it and take away the squeeze out. And some of the time with the squeeze out, you just want to lift it off of the surface. And even if it still clings there, then you can come back with a chisel later and just knock it off. Okay, so I'm ready for the next bar, and I'll just keep going down the line. So I'll put it into the heater. And of course, you want to be applying the glue to the face that you can see the grain lines, so that when the bar goes down, the grain is in the vertical direction relative to the plane of the soundboard. And you can always reposition the bars if you want to get a better distribution. And now the next brace is ready, and I'm going to put in the brace after that into the warmer. And it helps to number your braces so that you don't get mixed up or put them in order in front of you. You can also see that I don't really need any fancy type of sticks, just some very simple ones made out of wood, and if they break, then just make some more. But you don't need any fancy fiberglass ones or anything like that, and these work out perfectly. Okay, we're all done, and I'm just going to let this set for 2 hours, and then we'll come back and start working on the horizontal braces. This looks pretty nice now. I've got the vertical fan elements in place, and you can even see if you look along the braces that that dome is being established in this lengthwise direction. And what we need to do next is to apply the horizontal components, and that will start to establish even more doming in this other direction, so that when we're done, we'll get a nice distribution of this radius all the way around the lower bout. And let me just mention now that at this point, if I grab through the sound hole and then flex in this direction, of course, these are going to resist this with grain direction, and it is very stiff, and it's essentially at the same stiffness that it will be even when we apply these cross braces. But of course, if I grab it on the ends and I flex this way in the cross grain direction, there's essentially no resistance to the force in that direction. So we'll start to introduce stiffness in that direction as we add the horizontal braces. But at this point, let me let you hear how it sounds. And you can compare to the pre-brace sound. Here it is again. Well, that will give you a feel of what the bracing does to increase stiffness and therefore increase the pitch. But now, what I want to do is to get these horizontal components ready, and I have this transverse brace that will fit below the sound hole, and I've already shown you how I get the 28-foot radius on the bottom. And then I've added these holes to inlet these fan braces right here and here. And I've also pre-cut some scalloping on the bandsaw just to take away a lot of material. And then I'm going to apply this crossbar. This is 6 millimeters tall by 5 millimeters wide, and it's going to fit across the majority of these fans. And so what I need to do is to take away some of the material to allow a gap in this fan and this fan, and I'll just carve away material and then allow the bar to come freely through. But for this fan and this fan and this fan, I'm going to notch both the fans and this bar so that when I glue them in, they'll be interlocked. So let me show you how I do these operations now. Now with these sections cleared to allow this bar to pass through without crossing, now I need to mark the positions where they do cross, and I need to make notches to let them interlock. And with my razor saw, I'm going to cut the notches. And with these fan braces, I make the notch halfway through the top of the brace. And then you can just pop out the pieces to make the notch. With the notches done, you can put the bar in, check the fit, and then mark the positions on the bar and make those notches. The key is not to make the notches too deep so that when you lock it in, you don't have any gaps. So here's test fit, and it looks great. I want to make sure that everything is seated all the way down to the soundboard. And we're ready to glue this in place, as well as these other components, to finish off the bracing scheme. Here's the fully braced soundboard coming off of the deck, and what I love about this step is that it's really architectural in look. It's got a lot of structure, whereas before we just had what seemed to be a plate. But for us luthiers, we know from episodes 13 and 14 that we spent a lot of time to place structure in the plate by thinning it to get the correct flexibility. And now by adding bracing elements, we combine these two components to get an overall assembly that works in concert with each other to give us a final structure that gives us the final sound. And while to many players, structure to them, what they can see is only bracing, we see things as a whole. In fact, there are things on a more microscopic level like doming, which if I sight down the lines of each brace, I can see an obvious bowing signifying this dome that I built into the lower bout. And if I turn it over, I can see an obvious peak in the center, and I can see this uniform doming in the lower bout. And the cool thing about doming is that you can increase stiffness without adding any weight. And it's just another tool to change the stiffness of a top and get the final type of structure that will dictate the final sound. Now, if I take this fully braced top without doing any other alterations to it, and I flex it in my hands, it's really stiff. And we already know this because flexing in this direction, even before I put these cross braces, it was stiff. And in fact, the stiffness is just about the same because we wouldn't expect these cross braces to resist the force in this direction. However, if I turn it 90 degrees and I flex in this direction, it's super stiff by comparison, especially in the center region. And in fact, I can only feel give now on the wings where it doesn't have any of these braces crossing over. And I dare not even flex any more than this for fear of cracking it. So one thing I want to do right now is to have you hear how the tap sounds, and then we'll compare it to where how it sounded like before we put all the braces on. Let's have a listen. And compare now. And here it is again. Yeah, it's surprisingly musical at this point. It's really a pleasant sound to hear. We hear a higher pitch, but a very focused and musical sound that has a lot of sustain. But I know from experience that if we took this top and glued it to the sides and went with it without touching any of the braces, it would be too high pitched, too stiff, and produce a really bright sounding guitar. So what we need to do next is to shave the braces to do what I call carve away the stiffness, to refine the amount of now flexibility to get it down to a pitch that will be correlated to a good sounding final instrument. So before we do that, I want to put it on the deflection rig to show you how much stiffness we've added by adding this bracing system. So let's do that right now. Let's do some accounting and talk about what we achieved by adding these braces. What you can observe from the deflection numbers is that we more than doubled the stiffness in the width grain direction, and over here in the cross grain direction, the stiffness increased about 5 times, no doubt with the large contribution of the massive lower transverse brace at the waist. The magic of bracing is that it provides all of this rigidity and directional control with very little weight gain. In fact, you can see that the braces only comprise 20% of the assembly's total weight. This small percentage highlights the principle that the soundboard plate will always be the heaviest component of the soundboard assembly. Similarly, engineers will always support the floors of multi-story buildings using beams to save weight rather than making a floor thicker. This is exactly the strategy that is taken to an infinite degree in lattice brace guitars, where you support a super thin top with a large amount of bracing. Our remaining task is to refine the bracing to get the right flexibility and thereby optimize the resonances that will dictate the tonal character of the finished guitar. We'll talk more about the resonances at the end of the video, but for now, these are the target flexibilities that I'm after based on correlations to good sounding guitars that I've built. And within these ranges, for the sound that I want for the player I'm building it for, I'm specifically after the higher end of these deflections. In other words, more flexible in order to achieve a guitar that is very warm and rich. So now it's time to start carving braces and head towards these targets. The first thing that I want to do is work on this cross brace, which started at 6 millimeters tall, which allowed me to do the notching very easily. But I want to take it down to about 4 millimeters, which is coincident with the height of these fan braces. So I'm going to take a small plane to it. And now that I've reduced the height of that cross brace, I can feel that it's starting to give, and it's still stiff though, and we'll continue to reduce the stiffness in this cross grain direction by working this brace a little bit later, but what I want to do right now is to work on the cross-sectional shape of each brace. And I'm going to triangulate the cross-section of the braces, and what that will do is reduce the weight and reduce some of the stiffness. And while I'm shaving the cross-sections, I like to use this little piece of plastic as a protector to put against the brace and protect the soundboard from getting chiseled or scraped or planed. And so I'm going to start with just a small little finger plane. And if you don't have a finger plane, you can use a chisel. That works fine too. And then what I like to do is to finish the angle with a piece of sandpaper just backed by a rubber eraser. Now that the braces are triangulated, I'm going to introduce a lot more flexibility into the soundboard assembly by doing what's known as scalloping. That is to thin the ends of the braces so that there's better continuity of stiffness from within the brace and then into the free plate. So I'll start by doing some very gradual scalloping, and then as we go on, we'll introduce even more flexibility by taking more off the tops of the braces to achieve our final flexibility. At this point, things are looking really good, and you can see from the deflection numbers that we're already arriving at our target range. And at this point, I need to describe to you some subtleties that numbers simply can't explain. And this has more to do with how my hands are feeling. And I know it's really hard at the beginning when you're learning this kind of thing and you don't have the experience through many different guitars, what you're actually trying to feel. So let me describe to you what I do at this point. And what I'm trying to do is to get a sense of how the stiffness or the flexibility is distributed around the plate. And that's why just getting a number from deflection is not going to get us to that level of subtlety. So the first thing that I do is to grab the soundboard through the hole, through the sound hole, and grab it on the other side down in the lower bout's end. And I'm going to start by feeling the stiffness in each of these fan braces because I want to check the stiffness in this with grain direction first. So for example, I'm going to put my thumb on the end of this middle brace and likewise on the end on the other side. And I'm going to push, and I'm going to push my thumbs in this direction upward, and my fingers I'm going to pull down so that what I'm trying to do is force the middle section upwards to get that flex. Now you can't really see the flex, but I can feel it. And what I'm feeling for is the distribution of that flexibility along the length of the brace. And because I only took off some scalloping at the ends, it's not surprising that I feel the brace kind of stiff all the way across. And that stiffness, because I'm applying the forces on the ends, of course, I'm feeling most of the bending in this middle section, which is the apex of these forces that I'm applying. So it feels to me like it's not, the flexibility is not distributed enough along the entire length. In other words, I need to shave off some material off of not just the very end, but now working my way towards the middle of the brace and take off from the end, so that now what I'm hoping to achieve is a flexibility that feels more parabolic along the length of this brace. And I'm going to do that for each one of these braces, such as this spruce brace. This one, this particular one, which I would call fan number 2, feels like it's pretty decently distributed in kind of a parabolic distribution of the flex. So I won't touch that one too much, and it's already pretty flexible. And then I'm going to test in this one, which I would call fan number 4. In this particular one, it feels a bit stiff, much like the middle brace is. It feels like it's not flexible enough in a parabolic fashion. So this one, I'll end up carving off of the ends and work towards the interior as I carve. And then the outside fans feel plenty flexible. So yeah, I won't touch those either. But overall, when I do this kind of flexing, I feel a firmness that really is resisting my hands. But it also has some give, so it's not completely stiff that I can't move it, which is good. And that is consistent with the flexibility that we measured in deflection. So really what I'm doing at this point is to try to really modulate more of the mobility around the whole plate. And why? Well, it's because over the years I've found that this kind of mobility that's distributed is correlated with nice sounding guitars. And I'm not exactly trying to hit any particular resonant pitch at this point, but this flexibility and overall mobility will give me the type of sound that will be supple as the guitar transitions through the different registers and a smoothness that I'm after. So it's purely based on correlation at this point, based on my experience. And theoretically, perhaps there's a good reason for wanting to distribute the distribution very evenly, because if you look at how this plate can move, it's still very supple in different directions as I torque it. Now, of course, that will change as we glue this top to the back and side assembly. It will create boundaries, much in the way that this strong brace, this lower transverse brace, sets up a boundary, of course, so that you won't get the kind of flexibility exactly that I'm applying to the edges with the force that I'm applying. However, if you think that all the string energy is just coming from the middle where the brace is tying your string, the bridge is tying your string, then it may be even more important to allow the suppleness to be distributed all the way out to the periphery. And you wouldn't want sections of your braces at the ends to be stiff. You want them more supple so that it can set up different resonant modes to set up very easily. So theoretically, there's good reason why you might want to do that. And we'll talk about that in later videos after we attach the top to the sides. So let's go ahead now and work maybe the outer thirds and fourths of each of these braces and then see how it feels. I like what I feel now in this width grain direction. It feels very even now in these bars that I adjusted. So now let's consider the cross grain direction, which can be easily adjusted by adjusting these transverse bars, such as this middle bar that's often referred to as a Boucher bar after Robert Boucher, who made it very popular, and then these two closing bars at the bottom. So if I feel the flexibility or the stiffness distributed across this middle part, still very stiff and feels like one solid bar and not evenly flexing. So I know that I can adjust by taking off material off of the ends of this Boucher bar, and then down here with these closing bars feels also pretty stiff. So I'm going to work on those, but before we do that, I'm going to let you hear the tap so you can hear where we started. This feels really good in the cross-grain direction now, and I'm really happy about the way that this soundboard assembly came out. I think based on all the properties that I can feel, hear, and measure, it's going to make a really fine sounding guitar. So let's wrap up now by having you hear what the final tap tones sound like and compare it to where we've been, do some final resonance testing, and then have some final comments at the end. I think from that progression you can get a better feel of what's happening to our plate both physically and sonically as we go through this whole process. And now I want to have a short discussion on the frequencies that we hear when we tap. Why is it that we hear the pitches that we hear? So let's start by listening to the pitch of our soundboard that we just completed. In my ear, I predominantly hear this pitch. And when we know from previous episodes that there should be an array of different frequencies that we can excite. So for example, if I hold the soundboard up here and I tap in a different location, I hear predominantly this pitch. So this demonstrates that yes, we can produce an array of different pitches, but let's let the microphone and the computer using Visual Analyzer tell us what the pitches that are represented actually are. Sure enough, looking at this frequency response curve, we see the two peaks that I demonstrated for you at 152 hertz and 199 hertz. And so why is it that these peaks are prominent? And the answer is that each of these peaks, these resonant peaks, are associated with a favored movement that the plate makes. And why is it favored? Well, it has to do with how we built the plate. Everything that we did to the structure that alters either the shape of the soundboard, the thickness and weights that we used in preparing the plate, all the way down to the bracing and how we soften that bracing by carving, all of that adds up to how the plate will actually move at high efficiency. And this is going to be the topic of the next video, when I actually take this plate and attach it to a body to close a guitar box. But for now, let me introduce it to you and show you that you can actually see the motion of the soundboard plate as we excite it at these frequencies. And the way that these tops move is really the recipe for what we hear when the soundboard pushes air to our ears. The way that it vibrates at different frequencies is the magic mix, the recipe that in different amounts and different strengths and at different frequency ranges gives us what we consider the voice of the guitar. So let's take a look at what's known as Chladni analysis to see how these plates move. Ernst Chladni was a German physicist and musician who is considered the father of modern acoustics. In the 1780s, he wrote a treatise on how vibrating plates move. You probably know of his famous demonstrations where he sprinkled sand on metal plates and got the sand to move by activating the plate with a violin bow. The sand settles in lines called nodes because those are the boundaries where the plate is motionless, whereas the vacant areas indicate areas of motion. Today we know that these patterns are formed the strongest when the plate is activated at resonant frequencies, and we refer to them as modes of vibration. But back then, Chladni's contribution was a glimpse into a completely unseen and poorly understood process of how plates move. Fast forward to today, and we know that we can replicate Chladni's experiments with our guitars, but instead activating them through space with sound waves, which physically are air molecules. You've already experienced this phenomenon when you're holding your guitar and it starts to vibrate when someone talks to you or plays in front of you. All of this is now made easy with a computer directing sound to a speaker, and this is what we're going to do. Not only is Chladni analysis a lot of fun to do, it will give you a better connection to what your top is actually doing when it's vibrating. And it really takes very little kind of equipment to do. Very simple kind of components like foam blocks to suspend the guitar top or your guitar body on. You need some kind of indicator, and I just use black tea and I put it into a container that I have holes in to sprinkle it over the top. And then I have a speaker to send the signal, and this is just a Bluetooth speaker. It's easily handheld, and this is an Ultimate Ears Mega Boom model. And it's just powerful enough, but light enough to get the job done. And then you'll need some kind of program on your computer. This is a free one called Online Tone Generator. There are many of them, but it's just a way to dial up the frequency that you want and then send pure sine waves to your speaker. And then lastly, you need some hearing protection because it can get pretty loud when you turn your speaker all the way up to do the analysis. So let's actually try some and show you how this works. Let me interpret what happened on this soundboard. Since the frequency that activated the board is 152 Hertz, that means the board is moving up and down 152 times a second. The position of the leaves reveals where the plate is at rest, and areas on the other side of these nodal lines are moving in opposite directions. So the movement of this mode of vibration is relatively simple, where the large middle area of the lower bout pumps up and down like a single piston, and with the border areas oscillating in the opposite directions. Now you can see how the power of Chladni analysis is that it gives you information about frequency as well as patterns of movement. And like deflection, this information can serve as an additional marker to correlate to the sound of your finished guitars. My final goal of this whole top construction process is to target this particular mode of vibration to be between 150 to 165 Hertz. And in this case, I targeted the lower end of this range to achieve warmth and richness. And you remember, to do this, I stacked the deck by aiming for a relatively flexible top assembly. And now I want to move to 199 Hertz, which is where we saw and heard this other resonance in the frequency response curve. And this will show you that different resonances are associated with different movements in the top. By now you're getting the idea that top movements aren't random. In reality, they're very well organized, and you'll notice that they get more complex as you go up in frequency. In this case, the primary movement is a back and forth movement in 2 halves of the lower bout instead of 1. This pattern explains why it was initially difficult for me to hear this resonance when I first tapped the top here in the middle. That's because the middle is the location where the top doesn't like to move at this frequency. Only when I moved out to here in an active area did it want to vibrate at 199 Hertz. That's pretty cool, isn't it? Well, we've come to the end of the video, and I want to thank you for sticking with me through a lot of information. I don't mean to overwhelm you, but I want to give you a complete look at the whole soundboard building process so that you'll get a good feel from the conceptual and theoretical all the way to the sensory approach that can be just as important, so that you'll be better equipped to make better decisions when you go into the workshop and do it yourself. If you're a relatively new builder, I can give you encouragement that making decisions shouldn't be daunting, but part of the fun part of building guitars, because making decisions is what makes it very creative and personal. I wouldn't be able to make this video or do the process that I showed you without a good set of notes, and so I encourage you to take notes as you go along. And if you want some ideas on how to take notes and what notes you should take, then I refer you to episode 6 where I talk about that. But every builder emphasizes a different approach, and that's the beauty of Lutherie, is that there are so many ways to accomplish what we're trying to do. And so by building enough guitars, you will naturally find your own way. You'll find the approaches and the markers that will lead you to the sound that you're seeking. So I'll see you on the next video.